Okay, answer to your names, please. Amo?
Here.
Lassie here? Yes, he is. Bishop? Here. Brad? Audio? Chestnut? Coolwood is here. Erlinson? Gerard? Green? Kennedy? Leonard? Mohammed Boy? Spot is here. Solomon is here, and Swiss Stack is here. Okay, so we're going to start chapter 7, which deals with the atomic structure, and this chapter is going to, especially in the latter part, delve into my least favorite topic in chemistry, quantum mechanics. I'm still recuperating from those courses in undergrad and grad school when it comes to this topic. So it's my least favorite topic. Thankfully for you guys, you don't have to get into it as in much detail as I had to when I was a student. Pretty much a lot of the things, especially in the latter part, will be the result of quantum mechanical approaches for determining how the electrons are arranged in an atom, but you guys don't have to get into the actual math of it. Basically, what I'll be teaching you is the result of the calculation. So let's start off with basically an overview of how we arrive at our current understanding of the structure of the atom. Basically, way back when, and I don't know what years or centuries we're referring to here, but back in the day, people used to think that small particles like atoms, electrons, and so on, they behave like regular particles, regular sized particles, right? So therefore, their behavior will be governed by the laws put forward by Newton. And then some people did some experiments with light, and they realized that that is not actually the case. Small particles behave quite different. And this leads us to the quantum theory, which is more accurate in terms of describing the behavior of very small particles. And this led to the behavior, or I should say to the quantum view, which describes the behavior of electrons in atoms. So that basically is just a very broad description of how we arrive at our current understanding of how electrons behave in an atom. So the first thing I want to talk about is the discovery of the electrons. And electrons were first discovered in the form of what we call cathode rays. And this guy, Johann Hittorf, in 1869, he discovered the cathode rays by setting up this particular experiment represented by this diagram right here. So let me describe what's happening here. We have here an evacuated tube, right? So that's why it says here, this part here is connected to a vacuum pump. We have two electrodes here, the cathode and the anode, connected to, of course, an electricity source. Typically, a switch would be a part of the apparatus, the circuit. So when the switch is closed, what was observed was that there's basically a beam or stream of particles emitted from the cathode towards the anode, all right? And initially, the first conclusion we can come to based on this observation is that the nature of these stream of particles is that they're negatively charged because they're emitted from the negatively charged electrode, all right? And the other thing that was noticed about these particles is that they basically travel in straight lines, all right? So those are the first two things that were discovered. And of course, in science, typically when things are discovered for the first time, then all other scientists try to basically do some further investigations to find out, more about what was discovered first. So therefore, in this particular case, people were trying to discover the nature of these particles, in addition to what we know about them before, all right? So what was discovered is that these particles will be deflected in the presence of a magnetic field and an electric field, right? So this is a reenactment of the experiment here. These are the stream of particles here, and here we have a magnet, and you'll notice that the stream of particles are moving toward the magnet. And the same thing will happen if there was an electric field nearby. So with that said, and another thing that was noticed too about these particles is that when they hit certain materials, especially glass, they cause them to fluoresce, which basically means that it causes them to light up, right? So those are basically the initial things or properties of these particles that were discovered. So a guy by the name of J.J. Thomson, he decided to carry out some further investigation into the nature of these particles. So what he did was that he created a modification of the original apparatus that was used to discover these cathode rays, right? So what you see here is an evacuated tube. All of this here is an evacuated tube. We have our cathode here, and these, this particular electrode here is the anode, but it has a slit in the middle of it. So basically, when the cathode rays are produced, they will have enough energy to pass through the slit. And there's another piece of metal here with a slit here, just to get a more narrow beam, which passes through this region here. Now, this region, in this region, what we have here are two magnets, right? And you can adjust the field of the magnet so that you can adjust the path of the beam as it passes through that region. Also, in the same region, we have two plates, two electrodes that are connected to this circuit right here. And that space here provides an electric field. And again, you can adjust the electric field so as to, change the direction of the flow of the cathode rays, right? So that's basically the setup. And so this is what J.J. Thomson did. Oh, and by the way, here there's a scale here which is used to measure the angle of the deflection as it passes, as the beam passes through this region right here. All right. So J.J. Thomson, collected some data. And I remember when I, in my physics courses, because I minored in physics in undergrad, we actually went through the type of calculation that was done here. And what he discovered, based on this experimental setup and the data collected from it, was the charge to mass ratio the mass to charge ratio of the electrons. And he discovered that the mass to charge ratio is equal to 5.68, or I should say more accurately, negative 5.686 times 10 to the minus 12 kilograms per coulomb. Now, I don't know if you're familiar with this unit coulomb, but coulomb, spelled C-O-U-L-O-M-B, that's a unit of charge. Unit of charge. And if I'm not mistaken, it is actually the metric unit of charge, all right? So basically what this is saying is that for the electron, the ratio of the mass of the electron to the charge is equal to that value, right? Now, of course, scientists are not just satisfied with that. They like to know the actual mass and the charge carried by the electron. So basically, if you can determine either the mass or the charge, then you can determine the other one. All right. So another guy by the name of Millikan, he came up with an experiment, his famous oil drop experiment. And just to describe what's happening here, so basically, he has some oil here. I forgot what kind of oil is in this particular container here. And you have a design here which allows you to spray a fine mist of that oil onto this plate here. Now, this plate here has a tiny hole which allows droplets of oil to pass through. And then, so this is one plate. There's another plate here which has no hole. But these two plates are connected to an electric circuit outside here. So again, an electric field is basically produced here. Now, here we have a source of ionizing radiation. What that does basically is that it provides energy to knock off the electrons from the oil drop, and therefore the oil drop will have a charge. And because this will have a charge on it, it can be suspended between the two plates if you adjust the electric field to the correct value. All right. So based on that adjustment, so that the oil is stationary, and you have a telescope here just so that you can observe the stationary oil drop. So based on the fact that you can make it stationary, if you know what the electric field is and you know what the mass of the oil drop is, then you can determine the charge on the oil drop. And again, this is one of those things that we did in physics. We actually went through and did the calculation, and we can prove, based on the data collected, that the charge on the electron, based on the Millikan experiment, is equal to minus 1.602 times 10 to the minus 19 coulombs. All right, so that's very important, a very important discovery that was made by Millikan. And therefore, based on the mass to charge ratio and the charge that was discovered by Millikan, we can determine that the mass of the electron is equal to 9.109 times 10 to the minus 31 kilograms, right? So basically what was that we take the mass to charge ratio, I don't remember what that was, and we multiply by the charge, and that will give you the mass, right? So, yeah, here, go back to, okay, so 5.68 times 10 to the minus 12. So the mass to charge ratio was 5.68 times 10 to the minus 12 kilograms per coulomb. And the charge on the electron is 1.6 times 10 to the minus 19 coulomb. So when you multiply those two, let me just do this just to make sure. 5.68 times 10 to the minus 12. Okay. Multiply by 6, and the answer I got is 9.09. Well, they have 9.109. Pretty close. I rounded off this number and the number before, so that's the answer, right? So that's how the mass of the electron was discovered. All right. Okay, so that was one, that's a very important development, discovery that was made as a contribution to our understanding of how the atom or the nature of the atom, or in this particular case, the nature of the electron, which is a part of the atom. All right. So again, people started working on actually how the electrons are arranged in an atom. And the guy by the name of J.J. Thomson, he came up with his model. In some textbooks, they call it the plum pudding model. Or is another term, I don't remember what it is. But basically what he suggested is that an atom is basically a large sphere, which is positive, and embedded in that sphere are the protons, positively charged particles, which we now know as protons. So for example, he proposed that in the case of the hydrogen atom, which has one electron, that electron is embedded in the middle of that sphere, which is positively charged. And then in the case of helium, he proposed that the two electrons that are present in the helium atom are embedded in the sphere, but they exist along a straight line, with each electron being halfway between the center and the outer surface of the sphere. So this is basically his model for the helium atom, right? The two electrons embedded in the large sphere, which is positively charged, and the charge of this sphere here would be equal to, but of course, equal in magnitude, opposite in charge, to the total number of electrons present. And what he also suggests is that if you remove one of these electrons from the atom, then the other electron will simply move right to the middle of that sphere. So this is basically the raisin pudding model that was put forward by J.J. Thomson. All right. So again, people are not just satisfied with somebody putting up an idea and just leaving it as that. Experiments were performed to test this particular model. So this guy, an Englishman by the name of Rutherford, he conducted his famous gold leaf experiment. And basically what he did, just to describe what's happening here, you have this element radium, which produces alpha particles. Alpha particles are basically helium-4 nuclei. So therefore, we're talking about 4,2He. That is the same thing as an alpha particle, all right? So the radium here produces alpha particles, which are shot at a gold foil here. Now, what is expected if the plum pudding model was in fact true? What you'd expect is that the alpha particles being positive will basically be repelled by the large positive nucleus of the gold atoms that are present here, right? So therefore, you'd expect them to be turned back, right? What was actually discovered was that most of the particles will pass right through the gold foil, right? Now, some will be deflected at an angle, such as following this path here or this path here. And there's some that would even be turned back, such as shown by this path here, right? But the vast majority of the particles will pass right through the gold foil. So that basically contradicts the Racine Pudding model, the J.J. Thomson's model of the atom, right? So what Rutherford, the conclusion that Rutherford came to based on this experiment was that in fact the structure of the atom is such that there's a small nucleus, which basically is the most dense part of the atom, which has the bulk of the mass of the atom, and the wider volume of the atom will have the electrons spreading around, all right? So most of the volume would be occupied by the electron, but most of the mass will be due to the nucleus, which would be the center. And that makes sense because using this diagram here, we can understand why Rutherford observed what he observed, right? Most of the particles will pass, most of the alpha particles will pass right through the gold atom because they will not, or the chances of them encountering any, well, especially the nucleus will be very small, right? Because the nucleus is itself very tiny, right? Now, there are a few particles that will come within close proximity to the nucleus and therefore be deflected. And that explains why some of the particles are shown to be deflected. And then there are yet few that will come into direct contact with the gold nucleus and be turned back as shown by the path labeled number 4 here, right? But most of the particles, the alpha particles will pass right through because it's very unlikely that the particles will encounter directly the nucleus of the atom, which is positively charged, right? So that's basically another important step in terms of our understanding of the structure of the atoms and where the nucleus is, or where the positive part of the atom is compared to the electrons. Okay, so the other particles that were subsequently discovered, protons, was discovered as a result of calculations that Rutherford did with some other experiments. He was able to determine the number of nuclear charges, which are called protons. And this led to the introduction of the atomic number, right? Which represents the number of atoms, or I should say protons in an atom of an element, all right? And then about 20 plus years later, James Chadwick, another Englishman, he discovered the neutrons in the nucleus. Now, the reason why the neutrons were not discovered for a while is because they have no charge, right? So the technology that they had then would not allow them to detect the nucleus, all right? So, but back then, there was some suspicion that, okay, there must be an extra particle present. And the reason why this suspicion was there was because the mass of the proton and the mass of the electron was determined, but the mass of the atom is larger, right? That's what they discovered then. So there was some, question as to, okay, what's that extra particle? And James Chadwick was the person who discovered, I won't go through the experiment that he went through to discover the neutron, but he discovered the neutron. So now we know, our current understanding of the atom is that there are 3 particles, the protons, neutrons, and electrons, right? Let me quickly talk about mass spectrometry. This is a technique which basically separates positive ions in the gaseous state according to their mass to charge ratio. And this is very important, especially when it comes to chemistry, organic chemistry. For those of you who have to do organic chemistry 2, if I'm not mistaken, you're going to learn how to use the mass spectrometry data to help you to determine the structure of organic molecules. But we won't get into that. We're just going to get into a simple example of how this works. So what we're looking at here is called a mass spectrum. And I think, if I'm not mistaken, this is the mass spectrum of the element mercury. The atomic number of mercury is 80, all right? And of course, you have different isotopes of mercury. The mass number is, where is it?
200. 592.
Okay, so that would be the average mass, right? Because of course, like other elements, mercury can exist as isotope, right? So what this is showing you basically is in a sample of mercury, the mass to charge ratio plotted versus the relative number of atoms, all right, for the different isotopes, right? Now, in each of these cases, the charge will be +1. So basically, these numbers would represent the mass of the different atoms, right? So there are some atoms which have a mass of 198, some 199, some 200, and so on, all right? The most abundant isotope of mercury is 202, all right? Has a mass of 202. So therefore, this is the mass spectrum. Now, how do we get the mass spectrum? Basically, what we do, it's a bit complicated, but I'm just going to simplify it here. we convert the mercury atoms into ions, right? Well, first we have to convert it to a gas, because as you should know, mercury is a liquid. So we vaporize it, then we convert it to ions by knocking off an electron from it, right? And there, what we do next is have a stream of ions pass through a region which has a magnetic field. And the effect of the magnetic field is that it will deflect the journey of the different charged atoms or ions in a circular fashion, right? And we put here a photographic plate which allows you to basically see by the brightness of the lines that are formed, basically the different isotopes being reflected. And the intensity of the lines will represent the abundance of the isotope, right? So basically that's what's done here. The heavier atoms will have a more tight turn, like in this case here. Or I should say the light atoms have a more tight turn. The heavy atoms will have a turn with a greater radius. And that's basically the separation, the basis of the separation. And that's why we end up with the spectrum of mercury right here, all right? So as I said before, this is a simple example, and there's some other examples that we can look at, but we won't go into that. But basically, this is used to identify isotopes, and also can be used in organic chemistry in terms of structure determination. And I think that's all I'm going to say about that. Okay, so now we're going to get into wave motion, and you might be wondering, what does wave motion have to do with the structure of atoms? Well, the only thing I can say is we'll see shortly. What I'm going to say here is that understanding the nature of a wave is important. You're going to see how important it is in terms of determining how the electrons are arranged in an atom. So we're going to spend some time talking about the nature of the wave. And I'm quite sure we have all done this as children. You might have a rope attached to some fixed wall, and you stay at the other end of the rope and you move it up and down, and that generates a wave, which basically is a transfer of energy along the length of the rope. So basically the rope, if you focus on one particle of the rope, initially it will be going up until it gets to a maximum point, and then it will go down and just go back and forth like that, and you have the wave generated. So there are certain features of the wave that we need to learn about, which corresponds to certain features displayed by electromagnetic radiation, which we're going to talk about shortly, right? So as stated here, the wave is characterized by the height of the crest or the depth of the trough. It's also characterized by some other quantities, such as the wavelength and frequency, which we're going to talk about shortly. So now we're going to get into the wave nature of light or electromagnetic radiation. It turns out that electromagnetic radiation behaves pretty much in the same way as the wave that I showed you before. So it has certain properties. So this is a diagram showing you what is happening when you have light or any form of electromagnetic radiation moving in a certain direction. So this is basically showing you the direction of travel. And as the term says, electromagnetic involves electric fields and magnetic fields that are perpendicular to each other. So let me see here, the red line here, or the red wave, I should say here, represents the electric field component, and the black and blue wave here represents a magnetic field component. So they are right angles to each other, but they have the same frequency and wavelength, which we're going to talk about shortly. So let's talk about the wavelength. What is the wavelength of a wave? The wavelength of a wave is the distance between two consecutive cycles, or you can define it as a distance between two successive peaks or two successive troughs, all right? So the distance between this peak and the next peak, that would be the wavelength. And the wavelength can be expressed in any particular unit of length, millimeters, meters, nanometers. It depends on actually the type of radiation you're dealing with, all right? So that's the wavelength. So that's one characteristic of a wave. The other characteristic of a wave is the frequency. Oh, by the way, going back here, I forgot to mention it. So this symbol is what is used traditionally to represent wavelength, lambda, Greek letter, right? Looks like an upside down Y, right? But that's the symbol that is used pretty much in any science literature where you're talking about radiation and so on. That's a symbol that is used for expressing wavelength. Then we have frequency. The frequency by definition is the number of cycles of the wave that passes through a point in a unit of time. The symbol that is used normally for frequency is another Greek letter known as nu, even though in some textbooks I've seen them use F. So as far as I'm concerned, if you use F or nu, then either will do, all right? As far as the unit of frequency is concerned, the unit of frequency is called hertz. Hertz. Right? And the symbol for the hertz units is Hz, and the Hz unit is the same thing as seconds to the minus one. All right? So seconds to the minus one, hertz, same thing. Okay, so that's a unit of frequency. Okay, so another characteristic of a wave is the amplitude, right? Which is basically the distance between a line of no disturbance through the center of the peak of the wave. So so if we're talking about this wave here, the amplitude would be this displacement right here. From here to here. Right? So that would be the amplitude. Okay? So that's another characteristic of a waveform. Okay. So those are the three characteristics. The two that we'll be looking at mostly would be frequency and wavelength because they're actually directly related to each other, right? So basically this is the equation which gives you the relationship between the wavelength and the frequency. The wavelength and frequency would be equal to the speed of the wave. And typically, the frequency, as I said before, would be seconds to the minus one. The wavelength would be meters, and therefore the speed of the wave would be meters second to the minus one or meters per second. Right? So that's basically how you can calculate the speed of the wave. You simply multiply the wavelength by the frequency. Okay, so what you're looking at here is what we call the electromagnetic spectrum. It's basically a listing of all forms of radiation, and you can have them ordered in terms of increasing wavelength or increasing frequency. In this particular case, you have them ordered in increasing wavelength going from left to right. All right. So at the low wavelength or high frequency region of the spectrum, you have gamma rays, right? And then you have X-rays. There's some overlap between these two. And then you have ultraviolet, and then there's a narrow band here, right? That narrow band here represents the different colors of light that our eyes are sensitive to, right? So you have violet, indigo, blue, then green, then yellow, then orange, and then red, right? And you can use certain memory aids. The one I use is Roy-Biv to remember the order of the colors. So this is the order opposite to what we have here: red, orange, yellow, green, blue, indigo, violet. All right. And I remember reading somewhere, don't know how true this is, that among the human being species, only the females can tell the difference by looking between indigo and violet. I don't know how true that is. I'm more inclined to believe it's true because I don't know the difference between indigo and violet. So there's probably some truth to that. Then you have, after the visible part of the spectrum, you have the infrared, and then you have the different forms of what I call radio waves, FM radio, TV, AM radio, cellular phones, microwave, and so on. And then you have the extra low frequency radiation as well, right? So as you can see, and I stated down here, most of the spectrum is invisible to our eyes. We have to use instruments to determine or identify the other forms of radiation. Our eyes can only observe the narrow band of the visible part of the electromagnetic spectrum. All right. Okay. Another thing I want to say about electromagnetic radiation is that they all display wave-like behavior, and they all have the same speed in a vacuum. And that speed has been determined to be equal to 3.00 times 10 to the 8 meters per second. So that is true for all forms of radiation, including the light or the different colors of light that we can observe. So the difference between them basically are the frequencies and wavelength, because when they multiply, they're going to be equal to 3.00 times 10 to the 8 meters per second. And we typically use the letter C to represent the speed of any form of radiation. So we can rewrite the equation we saw earlier. Frequency times the wavelength is equal to C, right? And that is for electromagnetic radiation. Okay, let's see here. Okay, before we get to. All right, let me do this and then we'll look at some examples or look at your assignment question. So white light, this is a white light source, right? If you allow it to pass through a slit and then a beam of light emerging from there passes through a prism, and that prism could be made up of any transparent material like plastic or glass, right? What will happen is another term that I learned in physics, and that is refraction. What is refraction? Refraction is basically the bending of a light beam as it passes from one medium to the next, right? So in this particular case, the light beam, which is a white light source, which comes from a white light source, which is, it turns out to be a mixture of different colors of light, as you can see here. What happens is that the beam hits here, and then the different colors of light basically will diffract at different to different extents, right? So therefore, the blue light seems to have a greater angle of refraction, or I should say the violet light followed by indigo and so on. And therefore, based on the different levels of refraction, as it passes here and then emerges from the other end and projected onto a screen, you're going to end up with the visible part of the spectrum being displayed on the screen, all right? So this shows you that white light source basically produces light, which has a mixture of radiation of different colors, right? And that's basically the same thing that you'll observe in the rainbow, right? Basically, the rainbow is basically the same thing as you see here. It's the visible part of the spectrum resulting from the sunlight being split into the different colors of light by water droplets, right? So that's basically what happens in this experiment. Okay, we're going to stop here for the time being, and we're going to look at questions in assignment 7. So let me hand these out to you guys now. Very soon, let me publish assignment number 7 so that you can have access to it. There. So let me publish it. I mean, let's publish it. Happening with this. Now we're in this. Okay, so For now, we'll be concentrating on questions 1, 2, 3. No, wait, hold on. Let me- Okay, basically questions 1 and 2A. We can't do 2B yet. Now let me see, question 3. Okay, let's concentrate on questions 1 and 2A. So the equation that we'll be using in each case is the equation I introduced to you, which is C is equal to lambda times nu, all right? Remember, lambda is the wavelength, nu is the frequency, and c is the speed of light. So, for the first question, it says an FM radio station broadcasts at 95.5 megahertz. Calculate the wavelength of the corresponding radio wave, right? So based on this equation, we can rearrange it to get wavelength. So the wavelength, lambda, will be equal to c divided by nu, right? Now c is always going to be 3.00 times 10 to the 8 meters per second. Now nu is given as 95.5 megahertz. And if you remember, we said that the frequency here has to be expressed in hertz, right? So we have to convert 95.5 megahertz to hertz. Now mega means what? What does the prefix mega in the metric system mean?
A million?
Exactly. So therefore, to convert from megahertz to hertz, you're gonna have 1 megahertz down here and 10 to the 6 hertz above, and that's it. So let's see what this gives. 3 times 10 to the 8 divided by 95.5 times 10 to the 6. And according to my calculations, this works out to be equal to 3 sig, so 3.14 meters, right? And that's basically how that is done. All right, and in terms of the units canceling out, megahertz will cancel out here and here. This hertz here will cancel out 1 over seconds here. So therefore, you're gonna end up with meters as your final unit. All right? Okay, any questions about this one? Any questions? Questions? Any questions out there in Zoom? By the way, let me see who came late. Okay. Leonard, right? Okay. Okay, so if there are no questions on this, let me go ahead and clear this. And scroll down. So this question says, a laser in a CD player uses light with a wavelength of 7.80 times 10 to the 2 nanometers. So we're using the same equation here. It's asking for the frequency. We're using the same equation, but we have to rearrange it. So the equation, just to remind you, is C is equal to lambda times nu. So how would you calculate nu, the frequency? Nu would be equal to what? Based on this equation. C divided by lambda. Now C, as I said before, is always 3.0 times 10 to the 8 meters per second divided by lambda, which is 7.80 times 10 to the 2 nanometers. But now we have to convert that to meters, right? So what's nano? What does the prefix nano mean?
Thousands?
Nope.
No?
Nano? Remember, 1 nanometer is equal to 10 to the minus 9 meters. That's what nano means. Nano means 10 to the minus 9, or 1 billion. So in this particular case, we're gonna put 1 1 meter up here, and 10 to the minus 9 meters. I'm sorry, what did I say? I'm gonna put 1 nanometer below and 10 to the minus 9 meters above. Right? So let's see here. 3 times 10 to the 8 divided by 7.8 times 10 to the 2 times 1 times 10 to the minus 9. And then according to my calculations, and please correct me if I'm wrong, but I got rounded off the 3 sig figs 3.85 times 10 to the 14. And the answer would be in hertz or seconds to the minus 1. Yes, sir. Meters, because you want the nanometers unit cancelled, and this meter unit will cancel with that meter unit. Yes, 10 to the minus 9 meters is equal to 1 nanometer, because the prefix nano means 10 to the minus 9. All right? Okay, any other questions about this? Any other questions? Any other questions? Okay, so let's move on to discussing some other important aspects. Let me clear this first, because we need to talk about how we calculate the energy of radiation based on the frequency. So, all right. So this spectrum that we were talking about earlier, we call this a continuous spectrum. All right. Now that comes from white light, which is a mixture of all the different colors of light. Now, before we move on to the other type of spectrum. So important thing you need to recognize here, of course, is that the different colors of light represents different wavelengths and different frequencies corresponding, right? So I think I have some numbers here. Yes. So for red light, the wavelength is about 650 nanometers. For the yellow, it's 575 nanometers, I'm sorry, and so on and so forth, right? And of course, we can calculate the corresponding frequency based on the equation that we were just using to work the answers to the question that we were looking at earlier, all right? So you can use these numbers to calculate the frequencies for the different colors of light. Okay, now let's talk about a different type of spectrum known as the line spectrum. Now, in order for us to understand this, I'm going to describe what is happening here. What we have here is what's called a hydrogen lamp. Basically, it's hydrogen at a very low pressure that is contained in a tube. And in that tube, you have 2 electrodes, right? You have one that is connected to the positive part of the electricity source, and the other part, the other electrode in contact with the negative part, right? So basically, you have an anode and a cathode, so to speak, right? And then it's connected to the circuit. You have a switch, you flip the switch, and the hydrogen starts to glow, right? So you're going to get this colored, kind of pinkish red colored light emerging from your hydrogen lamp. If you pass it through a slit and then through a prism like you did before, and you project it onto a screen, you're going to get not a continuous spectrum where you have the different colors of light being transformed from one to the other as you go across the spectrum. Instead, what you have are defined light lines in the spectrum of different colors and dark regions in between it. So you have this line here, which corresponds to this line right here. Yeah, I don't know if you can see from where you are, but you have one other line here which looks blue, and I think these are either violet and or indigo colored line, right? So we call this a line spectrum, right? Which is different from the continuous spectrum that we observed earlier. And we observe a line spectrum being produced by elements that are placed in this sort of setup, right? And in fact, we can use a line spectrum to identify elements because it turns out that different elements will have different line spectrum, right? So just to give you some examples of some other line spectrum produced by different elements, you have mercury, this is the mercury one right here, you have lithium, you have cadmium, and you have strontium, right? And you can basically use these to identify a particular element. In fact, it is the use of light spectrum that is used to identify, for example, the presence of certain elements in stars by astronomers, right? They have their own unique instruments, which allows them to distinguish between different elements according to their light spectrum, and therefore they can tell, for example, like in the sun, iron exists up there as a gas, all right? Because they have identified the light spectrum of iron present in the sun, right? Okay, so that's basically the light spectrum that is produced by atoms. Now, how are these produced by atoms? Well, we have to go into some aspects of what we call the quantum theory. This guy by the name of Planck, he came up with this notion, this idea, that vibrating atoms in a heated solid can absorb or emit electromagnetic radiation, but only in small, discrete amounts, all right? And these amounts, called quantum, basically represent packets of energy, and the formula for calculating the radiation that is either produced or absorbed is this formula right here. E is the energy, is equal to H, which is known as Planck's constant, times the frequency, right? And the value of Planck's constant has been determined to be equal to 6.63. For all purposes, we're just going to run it out to 3 seconds. 6.63 times 10 to the minus 34 joules second. And please note that the units of Planck's constant is joules second, not joules per second, but joules second, all right? So we can use that formula to calculate the amount of energy that is either absorbed or emitted by vibrating atoms, all right? So according to the hypothesis put forward by Planck, basically it says that energy can only be absorbed or emitted by, as what is called a quantum, or as whole multiples of a quantum, right? So this represents the energy of a quantum, so therefore the energy of an object can be changed by either this amount or multiples, 2 times, 3 times, 4 times, whatever, all right? Multiples of that quantum, right? Okay, so that's as far as the quantum is concerned. Now, Einstein basically considered the quantum to be packets of energy, which are called photons, and the photon energy is given by the same formula, right? And there's this experiment which kind of lends credence to this. Let me quickly describe what's happening here. So what we have here is encased in this glass cover here. We have an anode, a metal, I'm not sure what the metal is, and then we have what is called a photoemissive cathode. Basically, this material will produce electrons when exposed to radiation of a certain frequency, right? So that is what's happening here. These two are, of course, connected to an external circuit, and as part of the circuit, you have this instrument here, which is known as an ammeter. It is basically used to measure the current, right? So if there's a current flowing through, then it will register that, right? So what happens here, and this is, I find it to be very interesting, what happens here is that when the photoemissive material is exposed to light of a particular radiation, electrons are produced, and those electrons actually travel through space from the photoemissive cathode to the anode, and therefore an electric current will flow to the external circuit. And as I said before, that will be picked up by the ammeter, right? So that's what is observed in this particular setup. Now, another interesting thing about this setup is that you will only observe an electric current if the frequency of the radiation is of a certain value or above. So if the frequency is above that threshold value, then a current will be observed. If the frequency is not above that value, then there's no current observed, right? And that is demonstrated by this graph right here. So the y-axis represents the current flow, the x-axis represents the frequency of light. Below the threshold frequency, there's no current, right? And then when you get to the threshold frequency, then all of a sudden you see a current flowing through the circuit, right? So the flow of the current is not dependent on the intensity of the photon. In other words, not dependent on the number of photons. It depends instead on the frequency of the radiation that the photon produces, all right? So that's basically what happens in what is called the photoelectric effect. Now, we're going to get to the connection between radiation and the structure of the atom. And the first person that came up with the idea of connecting the two based on the experimental observation of the light spectrum is this guy here. His name is Bohr, Niels Bohr. And he came up with a theoretical idea, a model of the hydrogen atom. Well, firstly, he found that the electron energy in an atom is quantized. And what does that mean? That means that the electron in an atom will have only a certain specified values, right? So basically, each specified energy value, we call that an energy level in the atom. And according to Bohr, each energy level corresponds to an orbit that the electron will occupy around the atom, right? So this is basically a picture representing his model, and his model works well for one electron atom, right? So you have the first orbit here, right? He calls that the n=1 orbit, and then you have the second orbit here. So what happens is that when the electron is in one orbit, it has a certain amount of energy, and then if it gains energy, it can be promoted to another orbit, and then it can be promoted to another orbit, and so on. Or it can start from here and jump several orbits into another orbit, 2 energy levels higher. So energy is required to make the transition from a lower orbit to a higher energy orbit. Correspondingly, when you have an atom, or I should say an electron, falling from a higher orbit, higher energy orbit to a lower energy orbit, then that corresponds to the emission of radiation, right? So according to the Bohr model, the radiation that we see emitted by the hydrogen in the experiment that I showed you earlier is due to electrons falling from a higher energy orbit to a lower energy orbit. When that happens, the amount of energy that is emitted by the electron will be equal to the difference in the energy of the orbits that the electron is making the transition from and to, all right? So that's basically what the Bohr model is all about. Now, quantitatively speaking, we can actually calculate the energies of the transition going from a lower orbit to a higher orbit or vice versa. And there's a formula which is used to calculate that. Now, this formula here, En is equal to minus RH over n squared. That formula is used to calculate the energy of a particular orbit. Now, n represents the number assigned to the orbit, right? So you have the first orbit, n=1, and n=2, 3, 4, 5, and so on. So that's what the n value is. And RH is a constant known as the Rydberg constant. Write this down here, Rydberg constant. I'm going to say more about this constant too, because you see different things in different textbooks, right? In this case, the Rydberg constant for the hydrogen atom is, again, for our purposes, we're going to round this off to 3 sig figs. So 2.18 times 10 to the minus 18 joules is the number that we're going to use for the Rydberg constant, right? So if you want to calculate the energy of the electron in the first orbit, then you simply put a 1 here. So that means that the energy is going to be equal to 2.18 times 10 to the minus 18. If you want to calculate the energy for the electron occupying the second orbit, then you put 2 here, so that's 2 squared. So it's going to be 2.179 times 10 to the minus 18 divided by 4, whatever that gives you, and so on and so forth, right? Very important for you to recognize the presence of the negative sign here, right? That indicates that there are forces of attraction between the electrons in the orbits and the positive nucleus, all right? What else? So if you imagine pulling an electron so far from the nucleus such that n represents infinity, that means the energy of that electron relative to the nucleus will be equal to 0, right? Because if n is equal to infinity, then En would represent or would be equal to 0, right? Okay, so we're going to get into how we can calculate the energy of the transitions, right? So basically, the difference in energy between the different orbits can be calculated based on the equation I just showed you. So this is the version of the equation which represents the energy of the orbit, the final orbit of the transition, and this represents the energy of the initial orbit of transition, right? So basically, the only difference between these two expressions is that the n values. This is n for the final orbit, this is n for the initial orbit. So the difference in energy would be, of course, difference between any two values would be the final value minus the initial value. So that's EF minus EI. And if we plug in these values into this equation, right, ultimately we're going to end up with this equation here. Minus delta E is equal to minus RH times 1 over the final n value squared minus 1 over the initial n value squared, right? So this is the equation that you can use to calculate the difference in energy of the transition as an electron goes from one energy level to the other, all right? Okay, so that's what we calculate delta E, the change in energy. And this is just showing you some,
Can we go back 1 second,
oh,
please?
sorry. It's okay, write it down.
Thank you.
Alright, so this diagram here basically shows you some transitions. And let me just say here, this is specific to the hydrogen atom, right? We're going to say more about other atoms later on. So basically, these are different transitions where the electrons are falling from higher orbits to lower orbits, right? So in the case of the electron falling from n equal 5, I'm sorry, n equal infinity to the n equal 1 and so on until you get to n equal 2 going to n equal 1. Collectively, we call these series of transitions the Lyman series. The Balmer series are the ones that we can actually see with our eyes. Excuse me, right? Where we have the transitions of electrons falling from higher energy orbits to n equal 2, right? So this is this looks like a violet or indigo line, that looks blue and that looks red, all right? Excuse me. So the colors that we see in the case of the hydrogen spectrum is due to the Balmer series of transitions. And then we have the Paschen series, which are dealing with transitions from higher orbits to n equal 3, all right? So, excuse me, our eyes are not able to observe the Lyman or the Paschen series, but we can observe the Balmer series with our naked eyes, all right? And over here, they're just showing you how to calculate the energy of each orbit, right? So in the case of the 5th orbit, the energy will be equal to minus, now I don't know where they use B here, this should be the Rydberg constant. So this should be RH here, minus RH divided by 5 squared. For E4, it's minus RH divided by 4 squared and so on, all right? In the case of the lowest, of course, n equal 1, that would be minus RH over 1 squared, which would be minus 2.18 times 10 to the minus 8. Excuse me. All right. Let's see here. Okay, so now, before I move on to okay, so now we can do some other questions in the assignment. We can do questions 2B up to and including 4C. So let's do that now. So let me go back to this. Okay, so let's look at 2B. So the question says calculate the energy of a single photon of this type. Now, the answer here will be based on the answer that we got for A. What was the answer for A again? Can somebody remind me?
3.85 times 10 to the 14th third.
So nu is equal to 3.85
Yes, sir.
times 10 to the
14.
and this will be hertz, right? So this question is asking for the energy of this radiation. So the formula for calculating the energy, which I introduced to you just now, is that formula. Energy is equal to H times nu. So in this case here, the energy will be equal to H. Now remember, H is Planck's constant, which by the way, I think it's in the packet that I've given you, so you don't need to memorize it. 6.63 times 10 to the minus 34 joules second multiplied by 3.85 times 10 to the 14. And this will be hertz, right? So let's see what that gives. Okay, so according to my calculations, this is equal to 2.55 times 10 to the minus 19. And the units here will be joules, because the hertz will cancel out with the second, because remember, hertz is the same thing, I'm sorry, hertz is the same thing as second to the minus one, right? Okay, so that's basically how the B part is done. Any questions about this? Any questions? Questions? Okay, can I clear this? So. Number 3 says microwave radiation has a wavelength of the order of 1.0 centimeters. Calculate the frequency and the energy of a single photon of radiation. So, I think I repeated myself twice here, so you can ignore this line right here, because that's repeated here, all right? Okay, so based on what we have done so far, let's hear what you have to say about this one. Let's focus on the frequency first. They gave you the wavelength, right? So how do you calculate the frequency based on the wavelength? What equation would you use? What equation would you use to calculate the frequency based on the wavelength? C is equal to lambda times nu, right? Wavelength times frequency. Okay, so the frequency would be equal to C over lambda, right? And C is equal to 3.00 times 10 to the 8 meters per second, divided by the wavelength, which is 1.0 centimeters. However, what do we need to do here? Because we have meters per second here, we have centimeters down here. So what would you do?
1 centimeter is 100th of a meter.
Exactly. So we're going to convert the centimeter to meters by multiplying by 1 meter above and 100 centimeters below. That goes with that, that goes with that, and that will give you your answer. You can do the calculation here, 3 times 10 to the 8, divided by. Okay, so according to my calculations, this works out to be equal to 3.0 times 10 to the 10, and the units here would be seconds to the minus 1, or hertz. So that answers the frequency part. How about the energy? What's the formula that you use to calculate the energy? What's the formula that I introduced to you just now to calculate the energy? E is equal to?
Negative RH.
No, not that one. H times mu, exactly. So in this case, it's H. What's H? And to the minus 34 joules second, multiplied by the frequency that we just calculated here, which is 3.0 times 10 to the 10 seconds to the minus 1. And that would give the energy. So let's do that. And according to my calculations, this works out to, okay, we have to run this off to 260. So I got 2.0 times 10 to the minus 23 joules, right? So that's basically how that is done. So that's the A part. Any questions about yes, sir? For what? Oh, this will be seconds to the minus 1. Sorry. Yeah. This would be seconds to the minus 1, or you can use hertz, right? Hertz, HZ is the same thing as seconds to the minus 1. All right. Okay. Any other question? Yes, sir.
In the 3.0 times 10, what is the power that you're raising that 10 to in the hertz measurement there?
Give me here.
Yeah.
That's 10 to the 10.
What's the minus 1 then?
That's seconds to the minus 1.
Oh,
What you just
so
asked about.
that's what you're saying.
Right, exactly,
All
right.
Thank you.
All right. Okay. Any other questions? Any other questions? Okay. So the B part is asking for the energy of an Avogadro's number of these photons, right? So this energy that we calculated here is for 1 photon, right? So how would you calculate the energy for an Avogadro's number of photons?
Multiply that by,
Multiply this by,
is it 2.33 times 10?
no, it's 6.02 times 10 to the 23. No worries, because these numbers will be available in Canvas, so. Where's my, okay, so it's 2 times 10 to the minus 23, multiplied by 6.02 times 10 to the 23. And according to my calculations, rounded off to 2 sig figs, that's gonna be equal to 12 joules. That's how you do that. Right? Okay, any questions about this one? Any questions? Any questions? So, I guess it's okay for me to clear this. All right, so what's next? Let's see. Okay, so it says here that the primary emission of mercury occurs at 404.7 nanometers and 435.8 nanometers. Says you have to calculate the frequencies of these emissions. So remember the formula is C is equal to, I'm sorry, yes, C is equal to lambda times mu, right? That's the formula, right? So how do we calculate the frequencies? Based on this equation, this is new equal to C divided by lambda, right? So we need to calculate this for each of these wavelengths, right? So for the first one, mu is equal to what? I'm sorry? But we have to start with C first, right? Oh, yeah, I'm starting with this, I'm sorry. Okay, what are you saying? Yes, I'm starting with the 404.7. So first we have to start out with the 3.00 times 10 to the 8 meters per second. And then we divide by what? 404.7 nanometers. And what do we need to do to this? Convert to meters. So 1 nanometer down here, 10 to the minus 9 meters above. See what that gives. So 3 times 10 to the 8 divided by, according to my calculations, the answer I got is 7.41 times 10 to the minus, I'm sorry, 10 to the 14. And the units here would be hertz or seconds to the minus 1. All right? And basically you do the same thing with the other number, right? Yes, sir. It doesn't matter. Same thing, same thing. All right? So I'll leave you to do the other number, but basically it's the same setup. The only difference is that you replace the 404.7 with the 435.8 here, right? Okay. Now B is asking for the energy. So let me remind you, the formula for energy for each of these photons is h nu, right? So I'm just going to do that for this one here. The energy for the first one will be equal to Planck's constant 6.63 times 10 to the minus 34 joules second, multiplied by this value here, which is 7.41 times 10 to the 14 seconds to the minus 1. Let's see what that gives. 6.63 times 10 to the minus 34 times 7.41 times 10 to the 14. And according to my calculations, I got 4.91 times 10 to the minus 19 joules, because this is going to cancel with that. Right. Okay, any questions about this one? Questions? And again, you do the same thing for the other wavelength as well. right? Okay, any questions about this one, the B part, what I just did? Question, we still have to do. Oh, yes, just you mean for the frequency for the other wavelength, yes.
Yeah.
The only difference is that you're going to use a different number there. You're gonna use the 435.8.
So there a second to a second answer.
Right, exactly. So you're gonna use the answer that you got for that one to calculate the energy for that one, right? Okay. Let me clear this. Scroll down. Oh, so this one is asking now, for you to calculate, let's scroll down. Calculate a mole of photons. This question is not clear. I think what the question is asking for is the energy for a mole of photons. Right, so make a note of that. Calculate the energy for a mole of photons of light with each of these wavelengths, right? So for a mole of photons, you know that a mole is Avogadro's number, 6.02 times 10⁻²3. So whatever the answer that we got out there in the B part. Okay, so what was the answer we got in the B part? 4.91, 10 to the -19. That would be joules, right? So we just multiply this by 6.02 times 10 to the 23, whatever that gives, that will be the answer. So 4.91 times 10 to the -19 multiplied by 6.02 times 10 to the 23, and round up to 3 sig figs. So the answer I got is 2.96 times 10 to the 5 joules. So that would be the energy carried by 1 mole of photons of light of that frequency. All right? Any questions about this one? Any questions? Oh, shoot, it's 10:43. Okay, I guess I'll have to stop here. Let me scroll down just to see what's happening here. Okay, so, yeah, we won't be able to do question number 5. Oh, yes, we should be able to do question number 5, but, okay, I would suggest you guys try question number 5. Let's go down. Okay. I wanted to try question number 5, and then we can discuss it. Next class. Yeah, that's what we're gonna do, all right? Okay, so I'll see you on Thursday. Right?
Yes, sir.
Okay. Just making sure. Yeah, you guys on there in Zoom, I'll be signing off.